All right, are you ready? Can you please close the door so we don't have to get the noise from the wall? Thank you. Okay, so let's continue talking about linear transformations. What I would like to get to, we'll probably get to it relatively quickly. What is the relationship between linear transformations and matrices, which is sort of interesting. Because you can think of matrices just like 2D arrays of numbers, right? That's also how MATLAB treats matrices, but there is much more to matrices, and that's what linear algebra and linear transformations essentially reveal. And that's what matrix multiplication follows from. So let's start where we ended the last time, talking about linear transformations. So let me quickly remind you what was a linear transformation. So linear transformation, first of all, is a transformation, right? So it's a transformation mapping function. I use all these words as synonym. There is no formal difference or anything, if you were wondering. So linear transformation is the transformation between two vector spaces, v1 and v2, which is linear. And the linearity means this. It means that it doesn't matter if you first do a linear combination of arbitrary two vectors v and w with arbitrary two scalars and alpha and beta, or if you first do them and then do the mapping, or if you first do the mapping or the transformation and then do the linear combination. I was trying to draw this diagram the last time. I'm sure I succeeded. So let me try to do a better one. It's basically the way to communicate this, or I guess even with this sort of clause here, to communicate this linearity relationship like graphically, if you will. So if this is my v1, and I have arbitrary two vectors, v, w, and I have v2, that's my, again, that's like my artistic license, right? Oh, sorry, I need to, you should remind me because I don't see this refocusing here. If it's doing that, I need to lock it so it's not, because otherwise it's quite annoying. Better? Yeah? All right. So I have a transformation going between v1 and v2. Oh yeah, thanks. If you did the name tags, that's great, because I still don't remember. And even if I know you maybe your colleagues don't know you, so that might still be useful. So you get to know each other too a little bit. Not that I would encourage that you talk to each other now. So T maps TV to some point TV, right? Or vector, to be correct. And the same thing with TW. And what this says, that it doesn't matter if I first do the linear combination of V and W, producing some vector alpha V plus beta W, and then map it. So this would be the result. This says that I will get the same thing as if I do the linear combination here. So if I do the linear combination of TV and TW, I get this point, which happens to be both T alpha V plus beta W and alpha TV plus beta TW. Does it make sense? I find it much easier to sort of remember these visual pictures rather than some sort of formulas with some symbol. The symbols are arbitrary, right? Of course, just like variables in programming. Okay. Yeah, and I think the last time I also mentioned a few examples, just really just scratching the surface. Very basic examples of linear transformations. So those were these three. It was just a multiplication by a scalar. Remember this? This was reflection, interesting type of linear transformation. Later we will see also rotation and so on. That's why it's so important, because lots of these nice operations which you need not just in graphics but everywhere else too, you can model using linear transformations. And also in applying an inner product, where the important thing here is to remember that the W vector is fixed. So that was chosen once and for all. And the V vector, that's a parameter, that's an argument of the function. So that's the idea here. All right, so trust me that linear transformations are very important. The big part of the course will essentially be about studying linear transformations. And we will start by studying how to represent linear transformations using matrices. So remember, the last time we also talked about bases, right? Maybe I should quickly remind you what the idea of a basis was. we didn't really define the idea of a basis precisely, but if we have an R to n dimensional vector, maybe I can just say the standard basis, just sort of, because if I have a vector space R to n, there I can pick what I call the standard basis vector. There's many different bases, but at least in the beginning, I don't think I need to complicate it any further and just stick with the standard basis vectors. Do you still remember how these guys look like? E1 looked like this. It had 1 here and zeros everywhere else. Similarly for E2, it was 0, 1, zeros everywhere else, and so on. You got the idea. I can also write it this way if I want to be a little more fancy. I, so that's my index, which standard basis vector it is. And there is a j that would be like the coordinate, the component. So this would be E11, E12, E13, and so on. Are you with me? So I could write that Eij is delta ij, where this delta ij is the Kronecker delta, which means exactly that it's 0 if I is not j, and 1 if I is equal to j. Have you seen this before, this Kronecker delta business? Oh, stupid question. Who has seen it before? Just curious. Some of you, about half, looks like. Okay. Just a little notational thing. Okay, so the idea of a basis is that if I pick an arbitrary vector v in Rn, I can find coefficients where the coefficients are real numbers, not vectors, so no arrows there, such that the vector v, vector v needs an arrow, right, is the sum or the linear combination. Now we can also remind ourselves what was a linear combination. It's the linear combination of the standard basis vectors. Okay, so what the basis does is basically gives us a way to measure coordinates. The easiest case, or the easiest way to visualize it in 2D, if I have some vector v here, this is my standard basis, which I usually call just x and y, but in this notation you could call it E1 and E2. E1 and E2 obviously nicely generalizes to higher dimensions, right? So what would be the alpha 1 and alpha 2 on this picture? I always like to see the geometric intuition behind it. The coordinates of this vector v with respect to the standard basis vectors. What are they? That's simply the orthogonal projection on each of the axes, right? So in this notation, this would be my alpha 1, and this would be my alpha 2. This length here. We discussed this a little bit last time, and we will have more to say about bases more accurately later on. But I just want you to get an idea. We could, even in 2D, we could have a different basis, by the way. There's nothing stopping us from having bases like this, for example, right? And then the same vector could be projected on that basis. And we will do lots of that later. The vectors would not even have to be perpendicular. They would not have to be orthogonal. That could still be a valid basis. We will discuss that more later. What I want to get to now is how to represent linear transformations using matrices. Okay. So the two ingredients we need there is the definition of a linear transformation. That's what I started with. That was this figure. And the idea of a basis. So if we put the two together, and let's do a 2D example first, because there everything is easier to write down. So if we take an arbitrary vector from R2, and we take the standard basis vectors, that's the E1 and E2, that's the standard notation for the standard basis vectors, then I can write the coordinates of V with respect to the standard basis as x and y. So what are x and y here? The type. You should always see the type of all these things in your mind. Someone can just yell it, that's okay. R, yeah, scalars, right? So x and y are just scalars, correct. Because they are not bold-faced, that would be one reason. So if I apply the arbitrary linear transformation t to the vector v, then by the defining property of the linear transformation, I guess I could put it like this, right? If I wanted to do really baby steps, x e1 plus y e2, right? And then from the definition of linear transformation, again, this property here, right? I'll apply exactly that. It doesn't get easier than that. And what I will get is exactly this, right? I can take the x out, and I only need to look at the image of the standard basis vector e1 by the transformation 2, and the image of the standard basis vector e2 by the transformation t, linear transformation, okay? So what this means is that the action of a linear transformation on vectors in R to n is completely characterized by its action on the standard basis vector. Sometimes they are called canonical basis vectors. So it means that to completely understand the transformation, all I need to do is understand what it does to the standard basis vectors. Okay? And it turns out this is very close to the idea of a matrix. Maybe let me first just write how the generalization to Rn would look like. I guess that's sort of straightforward if you think about it. So in Rn, we have the standard basis, which I just explained. So the vector v, if it's from Rn, so see it, yeah, that splits into x1 e1 plus xn en. If I apply the linear transformation t to v, then I can just apply this property like recursively, just one by one. And what I get is I do x1 t e1 plus, let me write it down really explicitly, and so on up to x and t en. Does it make sense? That's a direct analog of the 2D case, right? And obviously it still follows from this, because I can just do it one at a time. And this basically matrix vector product is essentially a shorthand for this. So instead of writing it this way, what I can do is assemble a matrix such that every column of the matrix will be the TEI. So starting with TE1, that's the first column. Second column would be TE2. You can guess how it continues. And we have the final one will be TEN. All right. And I can say that this is a matrix, and I multiply it by vector x1, x2, and so on to xn. So this basically is essentially a different notation for this sum. Let me again go back to 2D, where it's a little bit easier. And let me give you a specific example that should make it a little bit clearer. Okay. So let's take a look at this particular example. So that's just a 2D transformation going from R2 to R2, and it's a linear transformation. You could verify it directly by just taking the defining property of linear transformations and verify it. If you want to try it, yeah, go ahead. I think it's pretty straightforward. And here I want to do what I was saying before in general. So what I was saying before in general is that I take the standard basis vectors so in 2D, that means that E1 is 1, 0, right? And E2 is 0, 2. So I take the, 0, 1. I was on autopilot. And what I do, I find out what the transformation f does to the standard basis vectors. Okay. So this is the similar equation as I wrote before. Again, any vector can be written as coordinates x and y with respect to the standard basis. Here I have the action of the function of the linear function f on the first basis vector, standard basis vector, and the second one. So what is the action on E1 of f? That's what's written here, right? So how did we get it? Well, I just plugged E1 into here. So that means x is 1, y is 0. So I get 5, 2 here. Yep. if I plug E2 here, that means that x is 0 and y is 1. So I'll get 6 and minus 3. So that's what I got here, right? So it's the same thing, exactly the same thing as before with some actual numbers in there. Yep. By the way, I see a bunch of you are taking notes, which is interesting. It happened last year too, even though I was saying don't take notes, I'm recording it. An interesting idea might be to try to take the notes from the recording. I don't know. If you prefer taking notes here, that's fine. I don't have anything against them. Again, I just remind you that I will put this on YouTube as always. Okay, so let's keep going. So what I do now is I take these two vectors and I put them together to a matrix. So the first column of the matrix is the first of these vectors, the FE1, and the second one is the FE2, the 6 minus 3. So I will get this matrix. And basically this formula, x times the first vector plus y times the second vector, I can write as matrix vector multiplication. So this is the matrix, that's a general vector of some xy coordinates, and that basically means the same thing. That's how matrix vector multiplication is defined. I will have a more general definition of matrix vector multiplication on one of the following slides. Let me give you another example. So here is an example of a different linear transformation. So this linear transformation, that's the example when we pick a fixed u and v. You could imagine some concrete numbers there if you wanted. And the linear transformation is a dot product, right? So what is the type of this linear transformation? Well, it goes obviously from R2, right, to what? To R, right? So I can apply the same idea to it. I find what the transformation does on the standard basis vectors, on 1, 0, and 0, 1, okay? And once I've found that, I basically know what the transformation does on any vector in R2. So what does it do on 1, 0? Well, on 1, 0, it gives me a dot product of uv with 1, 0, right, which is just u. So this whole thing is nothing but u. It's just a scalar in this case. It could be a vector in general, but in this case, it's just a scalar, or R to 1 vector. And similarly, F01, what is that? That's obviously V, right? That's UV dot product 0, 1. Everybody sees that? I guess I don't really have a chance to try to remember your name, because maybe we need to do more interactive type of thing. So if I put it into a matrix, I guess that's because this is so simple, so I don't really feel I need to ask a lot of questions. If I put it into a matrix, I get a special type of matrix, which is just a one-row matrix. That's because this was only going to R. And the matrix just has the two numbers u and v, which were fixed here. So again, I can write it as a fairly special type of matrix multiplication. This is a row vector times column vector, which again means nothing that u times x plus v times y. It's another example of a linear transformation. Okay? Yeah?
To clarify here, uv is just one other vector?
uv, sorry?
No, in the beginning. So that uv is just a vector?
Yeah, if I write it like here together, then it's a vector, yeah, which contains two scalars. That doesn't matter here that much because the u and v are some arbitrary parameters I can pick arbitrarily.
Oh, so and it also could have been f of u and v as well, as it is f of x, y.
You could do that, yeah. I mean,
it doesn't matter, or it doesn't matter.
So here is, yeah, this is the thing. The thing is that the u and v sort of, like I can explain it like this. In programming, if you were doing a function, okay, I guess let's see if I can still write like C functions. I would have like a function f, which would put like float x and float y. Those are inputs to the function, okay. The function does something and then returns something, okay. And the u and v, those will be like global variables. They will be like here. There will be float u and v. That's like sort of using like a C notation. Does it make sense?
Oh, okay.
That's the idea. So sure, you can feed there u and v too, but the point is that x and y can be arbitrary, right?
Oh, okay.
Makes sense? All right, so this was just an example. What is important is the general definition of matrix vector multiplication. So I sort of already explained it, but here it's summarized in the general case. So we assume we have a rectangular matrix. Oh, by the way, this is how I will be denoting the set of matrices. Okay, I don't think I used this before. So this R means it's a real matrix of real numbers. Most of our matrices will be made of real numbers. Sometimes it will be natural to consider matrices of complex numbers, but those will be some special cases which I will notify you about. The first number always is the number of rows of the matrix, and the second is always the number of columns. So like this. So this is the number of rows. This is the number of columns. This convention is pretty much set in stone, amazingly. Oh yeah, it's actually written here too. M rows and n columns. So that's what this symbol means, that A is an M by n matrix. V is a vector, as before, right? That's our familiar notation. By the way, matrices, again by convention, to distinguish them from vectors and scalars, we usually denote with capital letters. Sometimes that would be capital bold, if you make it even more obvious. It's just a notation to sort of make it clear what is vector and what is a matrix. It's a little bit funny, right? Because sometimes you can look at a vector also as a matrix, so it's not. It's just a notation. And the matrix vector product says that if I multiply the matrix A with my vector V, I get a different vector W. The vector W even has a different dimensionality, right? Because if it's an M by n matrix, it means it maps n-dimensional vector to m-dimensional vector. Okay? And how the individual components of the vector are computed using this formula. So I guess the best way is to write it out, the matrix. So let me try doing it here. Is that well visible? I hope so. So if my matrix has elements A11, A12 up to A1, how many columns? N, right? That would be A21, A22 up to A2n, right? And it has how many rows? M. M1, M2, goes all this way, and the last one will be AMN, right? So this is my matrix A, written out all the individual elements. There is m times n of them. And the matrix vector multiplication looks like this. So this is the vector has coordinates v1 or components v2 up to vn. Always gotta be careful what is there. And now if you what does this mean? That means that the W is a vector of m components, W1, W2, up to Wm. And it's computed like this. So the ith component of the vector W, I look at the row number I in the matrix A, and I sum over all columns. Every element hitting with the corresponding component of V. So notice that these dimensions have to match. The number of columns of the A matrix must match the dimension of the V vector. Otherwise, this wouldn't really make sense, right? It's just like making the dot product. I can only make it a dot product between two vectors of the same dimension. Okay. So one way you can look at this is if I denote the row of the matrix as R1, the second row would be R2. Those would be like row vectors up to Rm. That will be the last row vector. So one way you can look at it that the W1 is the dot product between R1 and V, right? W2 would be the dot product of R2 and V, and so on up to Wm would be the dot product of Rm dot V. Is that clear? That's basically a different way to write down write down this sum. It's all about notation. So here I had to denote the rows of the matrix, and then this is a dot product. Okay. The funny thing is that there is a different way to sort of look at it. That happens actually a lot in the linear algebra. We'll talk about transposition. It will get even more interesting. The other way you can look at it is by looking at the columns of the matrix A. So if I say this would be my column C1, be column C2, and so on up to the last column would be C, what, M or N? N, right? So N columns, Cn. Then I can also write that the vector W is C1 times V1 plus C2 times V2 plus Cn times Vn, where those are just scalar products. So the second view on matrix vector multiplication says that the result of matrix vector multiplication is a linear combination of all the columns of the matrix A. And the vector I'm multiplying with, those are exactly the coefficients of the linear combination. That's what this equation says. Okay? So there are two equivalent views on matrix vector product. You can either look at it as inner products with the rows, so dot products with the rows, or a linear combination of the columns of the matrix. So, sorry, say again? Linear combination of the columns with the coefficients being the v vector, the argument, the vector I'm multiplying the matrix with. Okay? That's the same, by the way, in both cases, right? Here I'm doing dot product with v. Here I'm just doing scalar product with v, or the individual coordinates of v, to be like super exact. So I recommend you to like remember this mental picture that if you are doing matrix vector product, then you are like scanning the matrix one row at a time, and you are doing dot product to like this. And you can sort of obviously see that the two views are equivalent. I suppose that is fairly clear. Is that clear? Matrix vector product. That's also what MATLAB computes for you, right? This is fairly simple. If you are actually doing it computationally, it can get interesting if you want to optimize it. Like the trivial implementation would be via 4-cycle, right? But these days you want to use some vector operations, especially if you do it on the GPU, so you might like group force of these scalars and like optimize this. That's what MATLAB is good for, that it has all the nice optimized routines already available for you, so you don't have to be optimizing the linear algebra. Okay, so we are almost at matrix multiplication. So the next level from matrix vector multiplication will be matrix multiplication. So how do we get there? Very interesting. We start by thinking about composing linear transformations. So here's the thing. I have three vector spaces, v1, v2, and v3. And I have a transformation f going from v2 to v3, and a transformation g going from v1 to v2. Okay, so that's what's said here. So I have three vector spaces, and they are both linear. F and g are both linear transformations. So f takes a vector from v2 and gives me a vector in v3. G is another linear transformation, different one obviously, which takes a vector from v1 and returns a vector in v2. Okay, and of course, why I'm doing this? Well, I wonder, I can certainly take a shortcut and go directly from v1 to v3, right? This shortcut is usually denoted as EF compose G, the composition of transformations, which means apply first G and then F. So that means consume a vector from v1, G produces a vector from v2, then F takes over, consumes the vector from v2, and gives me a vector from v3. And if I combine the two together, I get the composed transformation F composed with G. Okay? And here is a simple, I wouldn't even call it theorem because it's such a simple thing. It's a simple fact that the composition of linear transformations is also a linear transformation. Okay? By taking this shortcut, I don't destroy the linearity. That's the point. Okay? How do I prove it? Very easily, as it's written here, right? To prove linearity, I need to prove that the action on the linear combination of V and W is linear, right? So here it sort of trivially splits into the two linearities. So the F compose G, so this is a notation, just a notation for apply G first, then apply F. By the way, start getting used to the weird fact that whatever is on the right goes first, right? So here it's F compose G, that means that G goes first and then F goes second. The same convention then will appear in matrix multiplication. I think it's very confusing. I'm sorry, I didn't come up with this convention. That's what pretty much everybody is using, even though it's counterintuitive because you read from left to right, but these formulas you have to read from right to left. Okay, so first applying G. Well, G is linear, right? So this is equivalent to doing alpha GV plus beta GW, right? But then F is linear again, right? So I can apply the linear property of F as well, and I get that this is alpha F composed with GV plus beta F composed with GW. So clearly F composed with G, I could also denote it as some H if you wanted to make it quicker. So this F composed with G is also a linear transformation, going from V1 to V3. Okay. Guess that's pretty simple. Now here's the cool thing. So this F, we know that now we know that every linear transformation can be represented by a matrix, right? That's what I was trying to explain here. Let me just remind you. So if I take the standard basis in the particular vector space, we are just talking about R2n and standard bases to make things simple. So if I take the standard basis, I can represent the linear transformation using this matrix, the images of the standard basis using the linear transformation. Okay. So I can certainly do it here for my F, and let's say this gives me some matrix B with respect to the standard basis in V2 and V3. And I can do it also for G. Oh, sorry, let me call this one A, and let me call this one B. So the B will be the matrix corresponding to representing the linear transformation G with respect to standard basis in V1 and V2. Okay. So I know that the action of F I can write using the matrix vector product, right? So if B is I'm getting confused in what is F and what is G. Because G goes first. Okay, maybe I wanted to have this as A. Just wanted to come out nicely. So that's why I worry about the notation. So yeah, so I want to first apply G. So that means AV. Okay, so it goes like this. So the matrix if I have vector V on input, then the result of the linear transformation is A times V, right? Matrix vector product, as we just discussed. Now, then the AV is just another vector, right? It's vector in V2. So I can apply F to it, but F is represented by matrix B, right? So that will be another matrix vector multiplication, right? So AV is just another vector, so I can certainly multiply it with a matrix, right? And here is the interesting thing. So I have these two matrices, A corresponding to transformation G and B corresponding to F. And because the F composed G is also a linear transformation, there must be some other matrix C which represents the entire transformation, F composed G going from V1 to V3, right? So how this matrix C is going to look like? That's basically what's going to be the matrix multiplication of matrices B and A, right? So sort of what you would want to do here would be to apply associativity and just do this, right? And then say that this is C. But we haven't still defined what would be the meaning of B times A. So that's what I'm trying to get to now, okay? So forget about this now. It's not allowed yet. It will be allowed in a minute once I sort of derive what the matrix multiplication should be, okay? And it's cool because we can derive it. Let me do the, it's sort of quick, so I will just do the math. I guess, how should I do it? Oh, but that's not the way I wanted. Yeah, I think I had it right at the first place, sorry. Because I wanted to be the product to be AB, not BA. So it matches with what I have on the next slide. So allow me to take it back and go back to original notation, which if there was, this would be A and B. Okay, so I get a nice AB. It's just a notational thing. Sorry about that. Okay, so let's take a look first at the BV thing. So that's applying the transformation G. That's the one that goes first, right? So let me denote the kth coordinate of BV like this. So BV is a vector, right? And I want to find out what is the kth coordinate of that vector. And by the definition of matrix vector multiplication we just discussed a couple of minutes ago, that would be this. So I'm taking the kth row of the matrix and then summing over all the elements of the matrix in the columns. So J goes over columns and multiplies with the coordinates of the vector V. Okay, that's just the matrix vector multiplication formula we had a couple of slides ago. Okay, and here comes the interesting thing. So if I now multiplied, so this result is a vector, right, which I'm multiplying with another vector. That another vector happens to be BV. Okay, again, I'm interested in coordinate number I of this vector. So this is how I denote it. This means this is a vector. Give me coordinate number I. Similar to like MATLAB notation. I guess MATLAB you would write the brackets there. So here I apply the exact same formula, except to this matrix vector multiplication. So here let me sum over K, and the matrix vector product in this case looks like this. So this would be the BV K, right? So here you can just blur your eyes and just assume this is some vector. Doesn't matter that it's BV at this point yet. Okay. So this is again just applying the matrix vector multiplication formula per element. Okay. And then what I can do, I can substitute for this form. So let me plug in this expression in here. And what I get is I get sum over K. Let me move the sum over here so the sums are nicely together. And here I have AIK, BKJ, and VJ. Okay, everybody see how I got that? I just really plug this in here. So here I get one sum, AIK, the second sum, but of course everything is distributive and commutative because we are just dealing with real numbers. So I can just put the sums together here. Okay. Now the interesting thing is, again, because this is really just a sum of some products of real numbers, so I can reshuffle it arbitrarily. Everything is distributed and commutative. So what I can do is I can switch the sums. I can first sum over J and then sum over K. Okay, and this I will leave as it is. AIK, B, K, J. And the VJ certainly stays there. Okay. And again, I won't change anything if I stick in brackets here. So basically this here what materialized here is a sum of, So this is basically a dot product of 8th row of matrix A with jth column of matrix B. Do you see that? Sort of need to the mental picture of the matrix. Always remember the first one is always the row index, the second one is always the column index. Okay? So as far as this sum is concerned, only the k is moving here. So here I am traversing a row of matrix A, and here I'm traversing a column of matrix B. Okay? So I can as well say, well, the k is just the internal parameter here. So I can call this number Cij. Okay? Just a real number. And if I do this, well, I find out I can just write it neatly like this, Cij Vj. Okay. Does this remind you something? What is going to be the last step? This is also exactly. This is just another matrix vector multiplication, right? With a matrix which I will call C, which is a matrix that contains the Cij's, C times V. So what we derived here is the matrix which represents the composed transformation. Struggling, how would I put it both together? Maybe like this. So I was saying what we are dealing with is a composition of linear transformations. First goes G, represented by matrix B. Second goes F, represented by matrix A. So it works like A times B times B. And now we know that if we define the matrix C in this way, so this is how the individual elements of C are defined, then I can say that A, B, V equals CV. Okay, sorry for the arrows. There we go. And this is nothing but the formula for matrix multiplication. So that's what the next slide is about. Is there any questions on this? It's everything is fairly trivial. You only need to wrap your head around the indices. That's the only thing there. So this gives me matrix multiplication, which is summarized on this slide. So I just did this so you can see how the matrix multiplication is derived, because it's such a simple thing. You basically just compose two linear transformations and you get matrix multiplication. And I guess all this why I'm doing all this is to convince you that the definition of matrix multiplication is not arbitrary. Because you could just say, for example, if you had two square matrices, you could be like asking, why don't I just multiply the elements pairwise, right? That would be also a good multiplication. Why don't we do that? Well, this is the reason, right? Because this matrix multiplication, as is traditionally defined in linear algebra, corresponds to composition of linear transformations. That's what I would like you to remember. Okay? So here is the definition again in a clean way. So we need to be a little bit careful about the dimensions. In linear algebra, almost always you have to be careful about the dimensions. So my A matrix will be L times M, so it means L rows and M columns, and B matrix will be M times N. So the important thing is that this M, this number of columns of matrix A, matches the number of rows of the matrix B. That's so that I can define the product of the two matrices, A times B. And the product will be a new matrix C of dimensions L times N. So see this picture again. So I am taking one matrix L times N, another matrix M times N, and what I get from it by matrix multiplication is a new L times N matrix. So you can like look at it as sort of annihilating this M in the middle. This is again like a mnemotechnic, how you can remember it, what the dimension of the matrix must be. And if these two were not compatible, again matrix multiplication would not be defined. Just like a vector, just like a dot product needs the same dimension vectors. Because after all, the matrix multiplication really is just dot products. If you think about it, as I said before, this is dot product between the row number I of matrix A and the column number J of matrix B. Okay, I guess I'll draw a picture. This is probably, oh, this is definitely worth a picture, so that you have again some sort of graphical mental model of matrix multiplication. Before I do that, let me just finish this slide. So this matrix C represents the composition of the two linear transformations, or more accurately, of the linear transformations represented by matrices A and B with respect to the standard bases. And here is one way to think about the C is as just a sequence of matrix vector products. Okay, I guess I will do the picture first. So let's say my matrix A looks like this, has this shape. So it has more columns than rows. Of course, the other case would also be possible. This is just an example. So this would be my matrix A. This would be my matrix B. Let me make it like long, so it's quite obvious that the number of columns is very different. So the L is the number of rows of A. M is the number of columns of A. So this is my matrix A. This is my matrix B. So the important thing is that the number of rows of B is also M. The number of columns of B is N. Sorry, this is M. Not my best M. It's sort of readable. Okay, so and the result of matrix vector multiplication is a matrix, how the matrix is gonna look like. It will have L rows, right, and N columns. So it will look like this. I really find having this picture in your mind, I find it helpful. You know that this is the same size as this, and these two, this length is the same as this one, and this one is the same as this one. So let me put it there explicitly. This is L, and this is N. Okay, so the result is L by N matrix. Okay, and the way how you can easily remember the matrix vector multiplication is that if I'm looking at I, J, ith row, so this would be row number I, column number J, what I need to do is take row number I and column number J and do their dot product. That's how I'll get the element here. That's why this M, the number of columns of matrix A, must be the same as number of rows. So this dot product actually works. The other way you can look at matrix multiplication, so staring at this formula for a little bit, you can realize something. You can, let me plug there 1 for J, okay? So if I plug there 1 for J, that will probably make it more obvious. A, I, K, B, K, 1, right? And let's just sort of forget about the 1 for a second. So what is this? It's just a matrix vector multiplication. Okay. So that's what's written here. One way to think about the matrix multiplication is to look at the individual columns of B. Let me denote them as B1, B2, B2, and so on up to Bn. And the result of the matrix vector product is essentially matrix product boils down to n matrix vector products, AB1, AB2, and so on. Sorry about the mess here, ABN. Okay, it's all in this formula. So I was sort of saying that if you sort of isolate this J, or just loop over J from 1 to n, then this immediately follows. Okay. So this is matrix multiplication, very elementary concept in linear algebra. I'll be using it pretty much all the time. So let's talk a little bit more about properties of matrix multiplication. So certainly matrices, or general about matrices actually. Because matrices you can also multiply by a scalar, right? It's trivial. Just like a vector you multiply by a scalar, you can multiply a matrix by a scalar. You can add two matrices of the same size together. So if the matrices must have the same number of rows and same number of columns, otherwise that would not be defined. And if I take these two operations, I can say that this is my scalar multiplication, this is my vector addition. So the set of matrices of a given dimension, m by s, the set of, okay, let me make it explicit, the set of m by n matrices for fixed m and fixed n is another example of vector space. You could go ahead and verify all the defining properties of vector spaces. It's, I guess, not that surprising because after all, you could also stack all the columns of a matrix into one long vector, right? So basically it's just like sort of different views on the same thing. The difference though is then on matrices we have the operation, we have the multiplication operation. That's not anything that doesn't have any analogy in vectors. We don't have any analogous operation on vectors. We have a dot product on vectors, that's the closest thing we can do, but dot product between two vectors always returns a scalar, right? If you have square matrices, and if you multiply square matrices together, you don't get any scalar, you get another square matrix, right? So that means the matrix multiplication that stays in the space of matrices, which makes it a completely different and very important operation. Okay. So let's look at some properties of matrix multiplication. I guess I will not bother too much with proving it. It's sort of easy anyway. So if I have three matrices, A, B, and C, with the right dimensions, and I have some scalars, then these properties are true. So the first one is associativity of matrix multiplication. It might actually be a nice homework if you want to do like an extra homework for you to try to prove that. So this says that it doesn't matter if I first multiply B and C and then multiply with A, or if I first multiply A and B and then multiply with C. The order here matters a lot because just on the next slide I will talk about the non-commutativity of matrix multiplication. So here you have to be careful about order. It's not like real numbers or vectors which are commutative. And the way you prove it, you just take the definition of matrix multiplication and you just put there another matrix. It will be massive indices, but at the end of the day, you will see that these two are exactly the same. The distributivity and matrix addition, and well, this basically means that scalar multiplication of matrices and adding matrices per element form a vector space. And here are distributive properties of matrix multiplication. So A times B plus C is the same as A times B plus A times C. Same thing applies for multiplying from the right. So because it's not commutative, I actually need to say this twice. I need to say it once for the left multiplication of B plus C and once for multiplying A plus B from the right. You see the difference? Because this is not the same. If it was commutative, this would be redundant. The one would be sufficient, but it's not. By the way, here I silently assume that all these matrix multiplications are defined so that these A, B, and C matrices are chosen so they have the right number of rows and columns. Okay. I guess it's sort of simple, so I guess I could spend like an hour sort of making this specific, but I don't think it's necessary. I think this is fairly obvious. So here's the thing about matrix multiplication not being commutative. So that means that AB does not always have to be BA, right? You can say, well, that's obvious, right? Because sometimes the dimensions just don't add up, right? As I said, if A is an M by N matrix and B is an N by L matrix, then product AB is defined, but BA doesn't make sense, right? Because B is n by L, so I cannot multiply but m by n, because unless L happen to be equal to m. Okay. But I could look at just square matrices, and in square matrices it does make sense to sort of form both products, right? If my A is, so let me write it properly. If A is n by n matrix and B is also n by n matrix, then certainly both of them are defined. AB and BA are defined, except that they are not always equal. What is the simplest example you can think of? 2 by 2 matrix. Or easier question, what is the simplest example where this happens to be true, like a very special case of matrices which actually do commute? Yes, identity, exactly. It turns out that a little less trivial example would be scaled identity. For example, if you take this matrix, also doesn't matter if you do this or if you do this. I assume A and B are 2 by 2 matrices now. So this will be equal because this is just a scaled identity. But the simplest example where it's not true, what do you think? Anybody? Can you please read your names and try to remember them? So the simplest example is already take a matrix 2, 0, 0, 1. Okay, and let's multiply it. So that would be 1, and this would be another 1. So this would be my A. This would be my B. So a quick exercise on matrix multiplication. So how do I compute it from my head? So I take the first row, dot it with the first column. So I get what? 2. First row, second column, again 2. Second row, first column, I will get 1. Second row, second column, I will get 1, right? What if I flip the order? What if I do first B, that's my B, and then A, 2, 0, 0, 1. So what do I get? First row times first column is 2, so far so good, right? First row, second column, well, that gives me 1. There's a problem out there, but let me finish it. Second row, first column, 2. Second row, second column, 1. Okay? So clearly these two matrices are not equal. So in this case, certainly AB is not equal to BA, even though both of them happen to be defined. I think that's the simplest example you can come up with. If you put there 2, 2, 2, 2, 2, that would happen to work, but that's only a very special case because this is just a scaled identity matrix. By identity matrix, I mean this. That's, by the way, the matrix of standard basis vectors. Oh, and as we are talking about linear transformations, to what linear transformation, that's like a quiz question, like do you want to be a millionaire? To what linear transformation corresponds this matrix with respect to the standard basis vectors? A to
the inverse? The inverse, is it?
It's a different no, it's simpler than that. You think there is a trick in it. There's absolutely no trick in it. Oh, okay. So it's even simpler than that. So if I have a 2D transformation fxy, what what is the simplest possible 2D? Exactly. It doesn't get really simpler than that, I suppose. That's the identity transformation. That's just the transformation that really does nothing to the input. That's a function of this type, right? I got into the habit of writing C code, so I can as well continue in. So that's a function that does this. I guess that's because I don't get to code so much anymore, so I will code during lecture. So that's identity, right? It's the it's stupid transformation, but it's an important case because it's a special case. So the identity matrix is matrix representation of identity transformation with respect to the standard basis. Okay, we'll eventually get used to the lingo of linear algebra. That's, I guess, what I'm doing here. Okay, let's do, now we have all this theory laid out. Let me show you a little more interesting example of linear transformations, okay, and their matrix representation, just to give it a little bit more juice. So the first thing is that I talked before about like more exotic vector spaces. If you remember, I talked about a vector space of all continuous functions, right? I think I also mentioned the space of all polynomials. So that's what I will be using in this example. So let's take the space of all polynomials with degree less than or equal to 2. That means all polynomials of this form. So what they are, right? They are functions from R to R, which happen to be writable in this form, typically look like something like this, right? You must have seen them probably even at high school. Polynomials of degree less than or equal to 2. So they have 3 parameters, A, B, and C, which I get to pick arbitrarily. And the space of all these polynomials of degree at most 2 is a vector space. If I define a scalar multiplication like this, and if I define vector addition like this. So obvious, right? By the way, our favorite identity, a function that looks like this, right, certainly is in that space too, right? What would I need to do to get identity? All what I would need to do would be to put A as 0, B as 1, and C as 0, right? Okay. Now, what would be a basis, an example of a basis in this vector space? It's a little bit tricky to talk about the standard basis, right? Let's forget about that notion. Let's just come up with some basis. Here, the natural basis seems to be x squared, x, and 1. So my function f1 would be x squared. It's really nothing but this, your favorite parabola. X would be the identity. So this is x squared, this is x, and certainly you know also how 1 looks like, right? That's 1. And every polynomial I can write as a linear combination of these 3 basis functions, okay, of these 3 basis polynomials. All right. So I have a vector space, a little more interesting example of a vector space, but it's perfectly valid vector space. I have a basis there. So any polynomial of degree at most 2, I can express using 3 coordinates, A, B, C, which are coordinates with respect to this basis, okay? So I just set up one vector space, and I need to set up another one because I'm trying to give you an interesting example, a different example of linear transformation. So I need to set up 2 vector spaces between which the linear transformation will be mapping. This is like my V1, and this will be my V2, and then I will show you a transformation that maps from V1 to V2, which will be sort of interesting. So my V2, the second vector space, is the set of all polynomials with degree less than or equal to 1. So they look like this, Bx plus C. Again, what would be the visual representation of this? How do they look like? If I always like to get the visual intuition, right? So what they are. Here I sort of drew like this parabola type of thing to give you an idea. In this case, it's even easier to say what they are. Somebody wants to say it, yeah?
Straight lines.
Exactly, yeah. Any straight line you can imagine. But actually with one exception, right? There's one type of lines that would not work here. Perfectly vertical lines, that they would not be there. But other than that, all lines are there. So vector space of all lines, if you want to think about it that way, is again a perfectly valid vector space. I can come up with the basis there, basis g1 and g2, x and 1, similar to the one we had before. And just like before, any function in this space can be written as a linear combination of these basis functions. And the vector bc, these 2 parameters b and c, which are by the way real numbers again, that are coordinates of G with respect to that basis. Okay? And then the example of a linear transformation between these two spaces, that will be differentiation. Okay? So I'm talking about continuous functions, specifically polynomials, so they can be differentiated. And it turns out that differentiation is a linear operation. Okay? And basically what my linear transformation is differentiating the polynomial from the first space, obtaining a polynomial in the second space. Okay? So if I denote differentiation by d, basically d means the derivative of f, you hopefully know from calculus that differentiation is a linear operation, right? That if I just, the definition of linearity would be the same as the, and differentiation is an example of linear transformation. So all we need to do to understand the differentiation of polynomials is to understand that's now we are sort of applying the theory we have previously derived in general to the specific type of transformation of vector spaces. So what I need to do is to find the action of the linear transformation on the basis vectors, right? The f1, let me remind you, f1 was x squared function, f2 was x, and f3 was just 1, right? So what are the derivatives? What is the derivative of f1? You must all know this, right? It's 2x. The derivative of f2 is 1, and the derivative of f3 is 0. Okay? So that's exactly what's written here in a sort of slightly different notation, where I already expressed this as a coordinates with respect to this basis, to the basis on this space, as I said here, is called g1 and g2 of x and 1. Okay? So here the 2x I represent as 2x plus 0. This would be 0x plus 1 and 0x plus 0. So this x is basically my g1. This 0 is my g2. It's a 0 times g2. And same thing here. This is my g1, g2. And the point is that after we do all this setup, the action of differentiation can be represented again using a matrix. And here from this you can sort of see what the matrix is, because those are the coordinates with respect to the basis vectors of the target vector space. So this is 2 and 0. So that's what I put in the first column of the matrix, 2 and 0. Here I have 0 and 1. That goes in the second column, and 0 and 0 goes in the third column. Now if you want to differentiate an arbitrary polynomial of degree at most 2, then all you need to do is take the coefficients of the polynomial and multiply it with this matrix. That gives you 2a and b, which are coefficients of the derivative of the polynomial. Okay? I guess it either might sound cool to you or it might sound sort of boring to you, depending on what your current standpoint is. But here it's basically just another example, slightly more interesting example of linear transformation, and that any linear transformation, even these more exotic cases, can be still represented by matrix. Okay, so I guess let me do a conclusion here of linear transformations. This is the concluding slide, saying that any linear transformation that maps a finite dimensional vector space onto another finite dimensional vector space, you can represent it using a matrix with respect to two bases defined in these two vector spaces. Okay, so we haven't talked much about finite dimensional vector spaces. Basically every R2n is a finite dimensional vector space, so that's fine there. And we we're focusing only on the standard bases, which are perfectly valid bases, but there is more general concept of bases. So it also works for different types of bases. Okay, So I think I will stop right here, and we'll continue this next Monday with the other topic, because I think this nicely concludes our discussion on linear transformations, unless you have some questions. Okay, then thank you.
So when you say linear combination, is the same as